Okay, good morning, everyone. Hope everything is okay. You're keeping warm and safe. And we'll start with the 7th lecture on quantum physics for non-physicists, and today is the 6th of October, 2020. Okay, so today we'll start with a bit of an overview of the lecture so far and the plan of where we're going, and then we'll continue exploring the particle in a line. But this time we'll do dynamics of a free particle. Just before this, we'll talk a little bit about how to expand from a line to three-dimensional space. So we'll talk about this a bit. And later, to do the dynamics of a free particle, we need an example of a state. So we'll talk a tiny bit about the wave package. So for these things, there's chapter 10 of the book of Schumacher and Westmoreland. It's not my favorite part of the book, in particular in the 3D states. I think we'll do things much more clear in the lecture. For the dynamics, though, we'll follow chapter 11, and this will be fairly straightforward. Okay, so the daily analogy, I kind of cheated because I'm running out of analogy ideas. So it's just what we'll be doing, which is, do you know, like when you play a video game and there's a tech tree of like you develop some technology and then you have access to some more things and so on. Like you discover the wheel, and then I cannot go into details, otherwise it feels like sponsoring again. Okay, so we'll do exactly this for the lecture. And for now, our tech tree is still very limited, but it's already impressive. So this is what we've been doing so far. On top, and at the bottom, it's what we'll be doing in the future. So we've been following, in general, like giving some formalism or some general rules for the quantum mechanics. And then we saw applications both in discrete systems and in continuous systems, where the discrete systems were mostly qubits or a series of qubits so far. Later, there'll be other ones. And the continuous systems were this idea of like a particle on a line. Okay, so what did we start seeing? First, we started with just the quantum formalism, right? That states correspond to vectors in Hilbert spaces, what Dirac notation was, how to compose different systems, what the notion of entanglement means, and then what are the rules for measurements, what are the probabilities of getting different outcomes, how can we represent them as both the measurements as projectors and as observables. And then we apply this to qubits. So we saw qubits in particular, so that they have can express a two-level system in many different bases, like the Z basis, the computational basis, and the plus-minus basis, which you call the X basis. We saw the block sphere representation. We saw how the different Pauli operators act on it. We ran a few little circuits. We saw this multiple systems by composing several qubits. We saw how to entangle qubits, etc. And in the case of the particle in space, what we've been doing the last week was look at expressing in the X and P basis, looking at the wave function for position and momentum. And then we started looking at the commutators. And today, as I said, we'll talk about 3D systems and also examples of such states. Good. Then what we did next was to start with dynamics. And first we talked just about unitary gates, like the Hadamard gate or the Z gate or the X gate or the C naught, right? Which is what we did for qubits. But we talked then about the Schrodinger equation in general, and then in particular about the case of uniform dynamics. So when the Hamiltonian does not depend on time. And then we started going into some specific types of Hamiltonians, some simple types of Hamiltonians, okay, which today will make even more concrete. So in the discrete systems, this was applied to, as I said before, circuits and entangling qubits. Also, we looked very briefly at rotating a spin. We looked very briefly at the toy example of how we can model a measurement. This was what ended up being Schrodinger's cat. And the rest of that lecture. And also in the tutorials, you talked a little bit about specific examples like trapped ions and interferometers, which we will cover in the lecture later on. Okay. In the continuous system, we look at this Ehrenfest theorem that tells us how position and momentum evolve over time. And today we're going to see the simplest example of them all, which is the simplest Hamiltonian you can have. And this is called a free particle, and you'll see these things in practice. So there'll be a lot of playing with commutators. Then there's another simple case, which I've not decided yet if I'll do this week or later in the lecture, which is a particle that is confined in a box. We'll see this later. But then we can start doing funny things by combining the discrete systems and the continuous systems. Like we said once, we looked at a very toy model example of the Stern-Gerlach experiment. That's when there's a spin that, depending on the initial state of the spin, the particle will go up or down. And we will do this concretely, so probably this Thursday even. Okay, so because it's a nice idea of like now composing a discrete system and a continuous system and seeing the dynamics on this. What we'll also have to do very soon is a double slit experiment. It's a very famous experiment in quantum foundations, and I'm sure you've heard about it. So this, after today, I think we'll already have the background needed to tackle this, so we'll do that. And then the next, this will be it for dynamics for now, I think, because then I want to start giving another big piece of background, which is how we model uncertainty. Okay, and this will be a lot, and we'll use it to do a little bit of quantum thermodynamics, which is it's quite cool. You'll study things like what's the smallest possible fridge you can build, and you can build it with 3 qubits, for example. Or what is Landauer's principle? It's about what's the work cost, how much energy you need to put into erasing information. So it's a very nice bridge between physics and computer science, for example. So we'll see those things later. And then we'll continue here with more concrete systems. So that's the overall plan, so that it doesn't seem like we're just giving kind of ad hoc content. You see there's it all comes together. Very good. So I'll start by recapping a bit of what we did last week about the line. Then we'll expand to multiple systems, and then we'll talk about dynamics. Okay, so last week we started talking about what I keep calling a line, and what this meant was just a Hilbert space that is given by a basis, which we call X, which is kind of a continuous basis. And we saw, I mean, that for a Hilbert space, you can choose many bases, and we were particularly interested in this other basis called the momentum basis. Okay, and such that they related in this way. We computed the inner product of position and momentum vectors, and it was, in general, you can trust me up to constants and minus signs, which is also constant, but I think this should be correct. And I told you that this h bar is a constant that appears in quantum mechanics. We could put anything there. There's something even called natural units in which you live. We just make h bar equals 1, so we don't worry about it. But it's just good to kind of keep on the back of our mind. And it's a constant essentially to make just a moment, so that we can, when we do measurements and we want to measure these things in units like meters and there's things in units like joules, then we need some kind of constant to, sorry, not joules, but units of momentum. Then we need some kind of constant, a physical constant that turns out to be very small to really transform from one to the other. So it's just kind of it's a translation constant. Okay, we saw how that the bases are related to each other via a Fourier transform, right? Same thing here, 2 pi h bar dp e IPX. Sorry. It should be the X. X, there you go. So we saw this. And then we saw that the wave function is really just we can expand any state in any basis. We can expand this state in particular in the position basis, and the coefficients are given by the wave function. It's again just a name. And then we saw how to transform from one to the other. And it's again always this constant behind. And all these integrals are from -infinity to +infinity. Okay, so I could write this here, but I will not write it all the time because it just gets very cluttered. Okay, so this is how we go from the position wave function, so, sorry, from the momentum wave function to the position. And the same here. So this is all old news. Dx E minus I P X H bar. And the minus comes from the fact that the P is on the bra, not on the cat. Fx. Okay. And then we spend a lot of time looking at operators and their commutation relations, right? And the reason why I'm listing all this here is because we're going to see how to generalize these things. So we have the operation x, which is just the x, little x. This is a cat and this is a bra. We have operator p. Same thing. For now, all these things are very symmetric, right? So it's even unclear why we call one position one momentum, and we'll see this is given by the dynamics. Then we wanted to see how it acts on the wave function. So this is just x self x. So it reads out the value x of the that cat. And now how does it act on the momentum one? Then so I think this is plus d dp, which we didn't do explicitly, so you can do at home if you like, but we did it for the momentum, right? So we saw that this operator p acts on the position wave function as this dx fx. We'll need this a ton today. And of course, it acts on the positional wave function just in the usual way. Up, hook, p, and should be a bar here just to remind us that it's not mathematically the same function. Okay. And then the last thing we looked at was commutators, because they'll be very important for dynamics. And the main thing is that x and p have the commutator IH bar identity. And then we could generalize a little bit. So we saw that if any function of p that can be expressed as a power series is given by dp f of p, and the same for the commutator with p. So f of x and p is IH bar d dx of x. Okay. This is all things we've done before. And now, before we see how do we expand this from having not just x, but also y and z directions, we're going to think a little bit about what's the analogy to qubits here. So I said that we start with qubits, and then we'll consider maybe d-dimensional systems, and eventually we'll make this d very large, and the spacing between the d's very small. And we will end up in the continuous case. So let's go back to like just the qubit and try to see what the analogy is. Okay, so let's put here the line and here the qubit and try to see what things are the same. So on the line we have this basis x. And then we have the basis p. And then later on, we'll want to have some kind of y and z. And naively you think, oh, in the qubit, there was the Bloch sphere. And then we had directions x, x, y, and z. So maybe it's the same. This is the analogy. And it's not, okay? And this is an important thing. It's really not. And this is more of an historical accident than anything else. So the actual analogy is to go from the x basis in the qubit, you can think of the 0, 1 basis, okay? Which we can call the computational basis. This because we call it computational basis because the elements, especially when we have several of them, several qubits, okay, and we can write them like this, like 0, 1, 0, 0. It reads like a bit string. That's why we call it computational basis. Okay. It doesn't have like funny plus or not. And the p basis, which is the Fourier transform, the actual analogy, which we'll see why, is with this transversal basis, the x basis, okay, which we can call this the basis x equals 0, x equals 1. It's what is called the x basis on the Bloch sphere, and this one is like z equals 0, z equals 1. Now I know it's very confusing that what on the right hand, what on the qubit is the x basis will actually correspond to the momentum on the line, and what is the x basis here corresponds to the z basis there. And I'm sorry, this is just a historical accident that it's called this way. Like these two different ways to develop this nomenclature were developed more or less independently, and when later on it was found that there was an analogy, they were already settled in their ways. Okay, so why do I say that this is the analogy? Well, let's see. How we can express these vectors in terms of the computational vectors. Okay, so if we take x equals 0, so that's just a plus state. What was this? So this was 0 plus 1 over square root of 2. And I'll give you a more complicated way to write the same thing. That this is the same as having here 1 and here another 1, right? And we can replace 1 with ei pi 0.0, 0 plus ei pi 0.0, 1. Why are you doing this, Lídia? I'll show you in a moment. Sorry, 0.1 here. If you want to express the state minus, which is x equals 1, in terms of Z of the computational basis states, that's 0 minus 1 over square root of 2, which we can express in a more complicated way as e pi 0, 1 plus e I pi 1, 1, 1 over square root of 2. Okay. So because this is just minus 1. So what this gives us is that some vector x is going to be, in general, is going to be the sum from all the z's from 0 to 1 e to I x z z. Okay. Which in this case, it sounds a bit silly to go through the trouble of expressing it with this exponential when the actual expression is so simple. But what this is a particular case of the discrete Fourier transform. Which is just a discrete version of the Fourier transform, which is something like this for an n level system. So if the dimension is n, and we had these two bases that satisfy this kind of relations, then we could go e to 2 pi I p x over n x, right? Whereas in this case, so this is the discrete Fourier transform. If then you take it to the continuous case, you get the usual Fourier transform as from that we saw in the line. And in this case, we just take, well, what we call P now we call the X basis state. What in the general case is X, here we call Z, right? And N is 2. So you see that this 2 will cancel that 2, and we get exactly this expression here. So this to say, the qubit, even in the qubit, you can have these two bases, which are related by a Fourier transform. What about the Y basis? It's again another type of this transform. So it's just another, it's just another basis, like another type of momentum, which we don't care about for the line for now. For qubits, it will be useful in some circuits, but we'll leave it aside. So then how do we do more dimensions? It's again, how do we do it with qubits? Well, we just tensor more qubits, right? How do we go? (3D), for example. So if you wanted to have 3 qubits, you just have, well, the first one, and then use the tensor product for the second one, and then use the tensor product for the third one, right? And here it's going to be the same because each additional dimension of space is going to be a new degree of freedom. So our Hilbert space in 3 dimensions, the global one is going to be an Hilbert space on X, tensor and Hilbert space on Y, tensor and Hilbert space on Z. Okay. And each of these Hilbert spaces is going to be exactly like the particle in a line, what we saw in the beginning. So what is a basis? I can say that the Hilbert space in 3D is the span of X on the system. Now whenever I remember, I'll make the subscripts explicit. So this is just to remind you that this is the first system. It represents direction X in space. Y, 1Y, tensor Z, and Z, where now each of these coordinates belongs to R, right? And sometimes instead of writing X, Y, and Z, we just write R, which is a vector, and it has already the 3 coordinates. So, so R belongs to R3. So R, we can express it like this. And what we mean by a vector R in the 3 systems is really just X on X, Y on Y, Z on Z, where I can just make this tensor product implicit. Okay, but I'll try not to because that's it can be confusing. So how do we get the momentum? We just do local Fourier transforms in each of these spaces. So each of these spaces is a line, so it has its own position, its own momentum. Okay, so we have the other basis, which is Px, tensor Py, tensor Pz, with Px, Py, Pz belonging to R. Each of them. And again, the same way we can call this vector P of X, Y, Z, where there's no need. Where P belongs to R3. So you can do exactly the same here. Okay. And how do we go from one basis to the other? Again, so the Px is the Fourier transform of dx. But it's so you see, it's a local transformation. It's not a global transformation. X, Py, it's going to be here. Y is going to be Y, and here is going to be Y. And if you want to do Z, it's going to be Z, Z, Z there, and Z here. Okay, so just really replacing. Okay. So what's the wave function then in 3 dimensions? So we used to have some psi of X, and now we need some psi of X, Y, and Z. And it's going to be exactly the same, which you can also call psi of vector R. By the way, sometimes some books use, instead of R, Q for position, and this comes from classical physics. So again, it's just a name. Okay, and how do we do this? Same way. So we just expand the wave function, which now lives. We expand the state, which lives now in the 3 Hilbert spaces. We'll say, well, the state is the same as having the state times the identity, and these are the identity operators for each subsystem. Okay. So what's an example of an identity operator for X? Well, this operator, right, is the generalization of just this diagonal matrix. And again, all these integrals go from minus infinity to plus infinity. Y times the same on Z, right? Now, integrals are just glorified sums. So we can take to the outside, we can take the sums to the outside. So we can take the chook dx, chook dy, chook dz. And what's inside? Well, it's going to be xx tensor y tensor zz. All of this multiplied by the wave function, which lives again by the state, which lives on the three systems. And now we just regroup things a little bit. Okay, so we'll just take all the cats to one side and all the brass to the other side. Which if you work out, if you write down like as vectors and columns, you see that you can do this. So we write here x tensor y tensor z. And here's x tensor y tensor z. And this is applied on this cat, right? Okay, and this is a number, right? Because the systems match up. So on the left we have x, y, and z. On the right, x, y, and z. On the right we have also x, y, and z. So the systems match up, which means that, and we know how to do the inner product into many systems. We saw this before. So this whole thing is going to be a number, and that's the wave function of x, y, z. Okay, which is a complex number. So we are left with what? We're left with this triple integral from minus infinity to plus infinity on all three dimensions, dx, dy, dz. Again, I can move the integrals to the outside. And then we have this psi of x, y, z. And then here we have x tensor product y tensor product z. Okay. And to simplify things, we can just write this as, instead of x, y, and z, we can just write r. So the D3 reminds us that it's in 3 dimensions. Psi of r, and now just remember that this is on x, y, and z. Okay. So you see, it's nothing special to go to more dimensions. It's really just a tensor product. Okay, so now we want to see if things still work out. So we will see that, for example, this what's the inner product between R and P? Okay, between these two vectors. Well, what we have here, so we have x tensor y tensor z on one side, and on the other we'll have px tensor py tensor pz, right? And we know how the inner product works over Hilbert spaces, we just do this one with that, times this one with that, times this one with that. So you get x px. Now this is a number, so we don't need the tensor product anymore. Y py is another number. Z pz, right? And each of these, we know what they are because it's just the inner product between x and p for each of the lines, right? So this is 1 over square root of 2 pi h bar, and here we had EIX px, and then the same. Sorry, I don't want to write it again and again. Okay. No. Okay. Y py z pz. Okay. And so the only difference really between the usual case of 1D and the case in 3D is one, this exponent here is different, right? You get the 3 from the 3 dimensions. And here you have I, and then what we have, x px plus y py plus z pz, which is just the inner product between these two vectors of R and P, right? But by definition. Okay. So in the tutorials, what you'll see is how to transform the wave function from the position wave function to the momentum wave function in 3 dimensions, which is just straightforward. And we'll also look a little bit into the operators, but I just want to write down how we define these operators. So what is px, for example? So px is px on the first system times the identity on the second tensor with the identity on the third system. Okay, just like we did for qubits. When we had a gate that was applied only on 1 qubit. And what you'll show in the lecture is that when you apply to the wave function, it maps the wave function on R to the usual thing, so minus I h bar d dx only of the wave function, and it leaves the other 2 components alone, or the other 2 variables alone. Okay, the same way we have py is what? It's just putting a py here. And it will act in a similar way, but for y. And pz is this. And just one that will be important later on, not today, but you'll do it in an exercise in coming weeks, will be, well, what is the operator p square? And this is important because it appears in the Hamiltonian a few times, right? And this is just going to be px squared plus py squared plus pz squared. But what we should remember is that these are these operators. So it's px squared tensors identity on y, tensor identity on z, plus the py squared. And it's good to at least once write down all the tensor products so we keep track of what we're talking about. Later on, when we solve problems in 3D, like when we start looking at atoms, for example, then we'll often just work directly with the wave function, and all the tensor products will be implicit, but it's good to see them in the beginning at least once. Okay. And you'll see how it acts on the wave function. So we'll see that in particular, P2 acting on the wave function, sorry, not X, but R. Let me write this down again. So if you have R, P2, and the state, this is going to be minus H squared. And here, all the derivatives. Right, so it acts just in the same way, and now we have a sum. And this will be important when you look at the dynamics of particles in 3 dimensions, and one of the terms is always going to be, it's always going to be just p squared, the kinetic energy. Okay, so this was recap, and it was a bit of extension into 3 dimensions. And now what will continue after the break is going to be with dynamics. Okay, we will not use 3 dimensions today. Maybe on Thursday we might use 2 dimensions, but we'll see. But maybe only the week after. Okay. So I'll just write here what we did last week. So keep that knowledge that you just acquired safely somewhere. And we'll come back to it later. So what we saw last week was, first we saw the Schrodinger equation for uniform dynamics, right? So this was at age psi of t was I h bar d dt psi of t. Then we saw that in general, observables, like the expectation value, the average value of an observable A evolves as, which means what? It's just this psi of t A psi of t. Okay. That this evolves as dA dt is 1 over h bar. And now the expectation value of the commutation with the Hamiltonian. Right. And then we saw a specific case of Hamiltonians. Which had just a kinetic energy and 1. So we had p squared over some constant that's related to the mass, plus some potential that depends on x. Okay, which could represent something like the an electric field, for example. That makes it very hard for an electron to be somewhere. And we call this the potential energy. And there's the kinetic. Right, and then we saw that for this kind of Hamiltonians, then we could write the wave function as, sorry, the Schrodinger equation like this. We just applied the operator p directly, and we saw that it was this square. So if we apply the Schrodinger equation to the wave function, we saw it was this plus v of x. This is a number again. multiplied by this number equals h bar d dt of the wave function. I'll let you go for a break in a moment. So let's just finish here. What we also saw was the theorem of how some observables evolve. So we saw that the average position evolves as p over mu, and the average momentum evolves as what we call f of x, the force, which is nothing but the derivative, the special derivative of the potential. Okay, this is what we did, and now we're going to, after the break, we'll start with a very specific case where we say, well, Vx is 0. We start with a Hamiltonian that's just this and see what happens. Okay, so I'll see you again at 1:45. Okay, welcome back. So before we continue, I'd just like to make two notes. The first one is that the Schrodinger equation is very general. This one is even only for uniform dynamics. We also saw the general case of the Schrodinger equation. And you could think, well, with this equation, we can solve all of non-relativistic physics, right? It is the same equation that describes the dynamics of every quantum system. So I think why I would need more, and the reason is that, well, it's still a differential equation. This Hamiltonian can have very complicated forms, like even this one is not too simple. And in practice, we can only solve analytically very, very simple cases. Okay, so for most cases of real life Hamiltonians, things can only be solved approximately analytically or with numerical methods, or lots of tools like perturbation theory, which we'll look a little bit into later in the semester. Okay, so while Schrodinger's equation is very powerful, we are often not powerful enough to apply it. The other thing is that you might have heard about Heisenberg picture and Schrodinger picture, and just because you might encounter this in other books, or even in this book, I don't know, I just wanted to write down what these two things are. And it's very, very simple. So the idea is that Schrodinger and Heisenberg, they came up with the quantum formalism more or less at the same time, but of course they did it in slightly different ways. So in the end, they're going to be equivalent, but they had preferences as to how they looked at things. So we can replace here the wave function at time t by just the wave function at time 0, and then it was evolved by some unitary at time t, right? Because it's the Bryce, the complex conjugate, it comes out our A, and then on the right again, we had the wave function at time t, and then it evolved overall at some, it evolved by some time t, where we know that this thing, in this case, it's minus I t over h bar, right? Something like this. Okay, and the thing is that essentially multiplication is associative. Multiplication of vectors is associative. And if you put the brackets like this, okay, then you have this object here, which is a sandwich between u dagger and u, which you can look at it as saying, well, we leave the state as initial state, and instead we evolve. What we're evolving is the observable. Okay? And that's Heisenberg's picture. So whenever you see that someone is solving some quantum system and they leave the initial state alone, and what they do is like evolve the observables themselves, it's Heisenberg's picture. Schrodinger preferred to evolve the states themselves, so Schrodinger would put the brackets like this, essentially. That's how we look at it now. Of course, that the formalism they had at the time didn't make it so obvious that it was this simple. Okay, so he leaves the observable alone, and instead he evolves the state. And there's whole discussions about which one of them had better taste, or which things are, which way of seeing things is deeper. This is Schrodinger, and this is Heisenberg. Okay, but really it doesn't, for now, it's not important for the kind of systems we're studying. It's not important. Okay, so that was it. So now we're going to look at the simplest case possible. I know that before, I think I accidentally called that general case free particle, but obviously free particle is only when the particle is not bound to any potential. It's only traveling under the weight of its own momentum. So we have h equals just p squared over 2 mu, and this mu is equivalent to the mass, right? So we know how to expand this in the p basis, because this is just the operator p squared. It's a capital P, by the way. So this is just minus infinity to plus infinity dp, small p now, squared, because we're looking at this specific instance. Okay. So as this Hamiltonian only depends on p, this means that the Schrodinger equation here, again, also only depends on p. So it tells us maybe instead of working with the wave function in the x basis, maybe it's just much easier to work with the wave function in the p basis to start with. So we do this. So we can see what happens, for example, when you have p, when you apply the Hamiltonian to the wave function. Well, this is just, I just take the Schrodinger equation, chuk, d dt, CFT, right? So I just took the Schrodinger equation, and then I kind of sandwiched, I topped it off with p on the other side. Okay. Well, this is the same as having 1 over 2 mu p squared, tac. And for now, we're only in one dimension. P. Well, the derivative on time does not, the p does not depend on the derivative on time, so they commute. So we put the derivative over time here, and then we have p side t. Okay, so this is just a wave function, right? So what we have 1 over 2 mu. This first term here, we know how p acts on the momentum wave function. It just gives you the momentum out, and you apply it twice to get square, the wave function of momentum. And here you have h bar ddt, and there's only again the wave function of momentum, right? So this is we can now move, this constant to the other side, but this looks now like a very easy differential equation. Okay, we only have the wave function itself on the, so some function on the left and the time derivative of itself on the right. So this is an easy thing to solve, and you can do it by hand if you want, but I can just give you the solution. So, which is I have p of t equals e minus I p squared time divided by to mu h bar, and the initial wave function. Okay, I'll put p and t equals 0. Okay, so how do we go? How do we go from here to x? Well, if you want to write the wave function in the x basis, then we just take this and we apply the Fourier transform. In this case, the reverse Fourier transform. I think one of them is the reverse, the other one not. But maybe we didn't start by knowing the wave function in the p basis. We started by knowing the wave function in the position basis. So we apply the Fourier transform to get this one. We evolve it in the p basis, and then we evolve it back. Okay. And just one more thing that we can do still in the p basis is to see, well, what's the u over t? You can read it directly from here, but you can also read it directly from the expression that we knew before. So it's more of a sanity check. So at minus I h t over h bar, right? And if we take now the form for my Hamiltonian, then this is just Tp E minus Ip squared T over 2 h bar. Okay. Which matches exactly this, right? Which matches this. Now if you sandwich it with a p on this side and the size 0 on this side, then you get precisely this result. Good, so this is a nice sanity check. Okay, so now we know how any initial wave function evolves, but we want to know how the physical quantities evolve. So if I measure the position at the beginning, and then I let it evolve freely, and then I want to find this particle again, so I go everywhere trying to measure the position, what's the distribution that I'm going to get? Okay, how will the average position of the particle have changed? How the average momentum have changed, etc. So this is what we'll do next now. So you look at the evolution of observables. And it's nice that we can do it in a simple case, and then later on we'll have to do it for more complicated cases. Okay. So of course, we could do it. We already have the wave function, right? So we could just apply this directly, but we're going to go through this way. So we're going to apply Ehrenfest's theorem to see how it looks like. Okay, and then we'll apply it to a specific case of an actual initial state. So first we'll do the average, which is also called sometimes the expectation value. So what's the dt of p? Well, this was given by this, right, which was just ddx p of x, but this is 0, which tells us that the momentum at some time t on average is just the initial momentum. Okay, which makes sense if you think of it as it's really a particle that it's totally free, it only has kinetic energy, and in this case we have conservation of momentum. There's no other forces acting on it. Okay, so then let's see ddt of x at some time t. Well, as we saw from the Ehrenfest theorem, this was just p over mu, and that's just initial momentum, which tells us that if this is a derivative, then xz times t is just the initial x times 0 plus this thing, mu multiplied by t. Okay. Which, again, still makes sense with classical intuitions. If something is moving linearly with some momentum, then here's the x0, which then the average position will also move linearly. Okay. But now let's look at what happens to the variance. And here it's going to become a bit more complicated. So now let's do it on the next page. And remember, what's the definition of variance? So for an observable, it's just this minus this. And it gives us sorry, this should not be a P, it should be an A. It gives us a measure of how spread out this is. So for example, if so if these are the possible values for the eigenvalues for A, for example, different X or different P, and this is the probability of measuring that outcome. And suppose we have a function of this kind, I don't know. Okay, oh, this is a bit ugly. Okay, well, one would be somewhere here. Then we'll see later a specific example. This should be more or less the delta A. Okay, and here would be A. So for well-behaved probability distributions, this measure that we're defining here really measures how spread out the distribution is. Okay. So again, remember, when we measure the position of a particle, this is given by a projective measurement. There's different probabilities for different outcomes. We can represent them as an observable, and from the observable, we can go and see what the average value is. And that's what we're doing here. Yep. So we start with the average the variance of the momentum, and that's just going to be p squared of t minus p of t squared, right? But each of these we know it's constant, right? This one we already saw that was p0, p of time 0. And this one, I mean, it's, I don't want to say obviously going to be the same, but we can do it by hand by just doing, well, d dt of this observable. This is just 1 over h bar of p squared and the Hamiltonian, but the Hamiltonian is itself just p squared. So this is just going to be 0. So this does not change in time, which means that p squared of t is just the initial p squared. Okay. So if these two values are just the initial values, then the variance is just initial variance of times 0. Yeah. So what this tells us is that if you look in the momentum basis, nothing is happening to the particle. right? If you look in the momentum basis over time, the average P is not changing, it's just a P0. And also the delta P is also not changing. Okay. But what happens in the position basis, and this is where we're actually going to find a difference, which in our case, because it's a free particle, I don't know if it will mean much. So it will just mean that the particle, even if it starts relatively localized, we'll see an example later, it will become kind of spread out in space. So still moving, but getting more and more and more spread out. And we'll see later some examples of more interesting physical systems with different potentials where this will actually make a difference. Okay, so then let's do this. So we have delta x squared at some time t. This is going to be x squared time t plus x, like this. And this one we already did. So this one was just a x t0 plus b t0. Sorry, let's write here 0 p0 over mu t squared. Okay, we're going to leave this one alone for now. We'll pick it up later because it's the simplest. So let's try to work this one out. What we know about it, well, we know how to compute the derivative like we did before. So d dt of x squared is going to be, sorry, 1 over h bar. And now comes the commutator between x squared and h. So that is 1 over 2i mu h bar. And now comes the commutator between x squared and p squared. Chuk, chuk. And then we take the average at time t of this. Okay. Good. So how do we solve this commutator? And now here we make a parenthesis. Helpful trick. Which is going to be the following. I'll write it down and then we prove it, okay? It's for commutators in general. So if we have A, B, and C, this is equal to A, B, C plus A, C, B. And we're going to use this because we know how to take the derivative of x. We know how to do the commutator of x and p. We even know of x and p squared because p squared is just a function of p. But x squared and p squared sounds a bit annoying, so I'll just say this general tool and we'll use it many times. Okay, we'll use it now, but also many times. And to see that this is true, we just expand the second part, and it's a, and then bc minus, or let's even do it like this. So this is a bc minus a cb plus, and on the other hand, we have acb minus cab, right? And these two cancel out. So that's ABC minus CAB, which is precisely that thing up there, right? Okay. So we're going to use this now. Helpful trick. Then we need to compute x squared and p squared. Okay. And I'll just write this as, for example, x p squared. So I know now that this is x times the commutator of x and p squared plus the commutator of the other x and p squared x. Am I right? Yes. I just took, this is like our A and this is like our B. Okay. But the commutator of, there's another helpful trick that we did before, that we know that x f of p, this is just I h bar d dp of f of p, right? We went over this again in the beginning of this course, of this class today, how to do this commutator. Good. And what's the derivative of p squared? That's just 2p. So we get here x I h bar 2p plus, same thing again, I h bar 2p x. So we get I h bar 2 I h bar xp plus px. And now we need to plug it together again here. Okay. And some things will cancel out, so I'll do it in the next page. But you can see already like the 2I h bar will cancel out with this. So with d dt of x squared equals 1 over mu, and then the average of this, which is going to be, sorry, the average of xp plus px. Right, good. What does this tell us? Not much yet, right? Again, remember, we're trying to find the variance. How does the position of the particle change in time? And in order to do this, we needed to compute this first term. So we took the time derivative. And we found something that it's actually the anti-commutator of x and p, and it's still a bit big. I don't know how to work with this, but given the magic of other people have solved this before, we know that if we take the derivative again, now we're going to get something more reasonable. Okay. So because we'll reverse engineer this, let's take the second derivative of this. I'm not sure you can take a lesson from here into general life that if you don't know what to do after the first derivative, do it again. More often than not, you may just end up with a mess, but let's do this again. Okay. So then this is just ddt of the thing here. Okay, so now we'll do this. Well, this is just a new observable, so we just apply Schrodinger's equation to it again. So ddt of that thing of xp plus px. Guess what? It's going to be 1 over IH bar. And now here again, that thing, xp plus px, and the Hamiltonian. Right. Which again, it's going to be 1 over 2I mu h bar, xp plus px, and now we have here p squared. Now, because everything is linear, we can do this as 2I mu h bar, and we can split this. So let me write it here. A plus B, C. This is AC plus BC. I'm not sure if we show this in the previous class, but if not, you can try doing it by hand. It's very, very simple. Okay, good. So we have this xp and p squared. Chuk plus commutator of px and p squared. Okay. And now what we do, we're going to apply the nice trick again. So let's do the first one. And I know it sounds tedious, but it's actually quite fun to solve them. So here I want to apply the helpful trick from before again, this thing here, where now A is going to be an X and P is going to be B. So that's X P squared plus X P squared P. But this we know is 0 because P commutes with itself and any powers of itself. And this one we just did before, right? We did it here. 2PIH. So we get 2IH P squared, P times P, which is 2IH P squared. There you go. This comes from the commutator, and this P was there already. Good. We do the other one, and it's exactly the same. Px P squared. So we take here P x P squared plus P squared x. This is 0. This one we know what it is. So we get, again P times 2IH bar P. Okay, which is again the same, 2IH bar P squared. Okay. So now we want to plug it in here, right? And I'll do it on this page still, and then we'll move it to the other page. So I have d dt of xp plus px. This is going to be, okay, so one term plus the other, we're going to get 4. So we get overall 2 over mu p squared. Right. And p squared at time t, which is, we know that time p does not evolve. So p squared at time 0. Okay, so now we can plug this in here. Okay. We're going to bring this whole thing up there. So we'll end up with d squared dt squared I promise that most research in quantum mechanics, well, at least in quantum information, does not involve as many derivatives. So is 2 over mu square now. And p square times 0. Okay, which makes sense because here we have momentum square, that we have here the mass square as well to cancel out those units. Good. Okay, so now we have the second derivative of our function is a constant. And now finally we have a differential equation that we know how to solve. So we get a second degree formula for x squared of t. So this is going to be now 2 over mu square times 0 plus some t squared, right? Plus some constant t is a t. That's a plus. Plus some other constant d. Well, this d is just the initial x as x squared. So that's this. And this c should be just the derivative of x squared at time equals 0, which we know what it is because we know that at time equals t, it's going to be this. So you just need to take this commutative for the value. Sorry, this average for the value t equals 0. Okay. So this is 1 over mu. And here comes xp plus px at time equals 0. Okay. Let's just put it all together. P squared, 0 t squared, plus this thing, xp plus px times 0 t plus. So where did we start? What were we trying to do again? We were trying to compute the variance of x. So we go back again to the variance of x squared. This was x squared minus, again at some time t, minus x squared some time t, right? And now it's time to go and pick up again, well, this thing here. Okay, so let's pick it up. Try, copy, paste. So that's what this is. And now the nice thing is that this is an average, it's a number. Okay, so this whole thing is just x0 squared plus p0 squared t squared mu squared plus 2x p t at time 0 over mu. Okay, with there's a time here. Okay. Good. Okay, so now we can put these two things together. And again, it's just a matter of annoying calculations, and I'll just write down what the answer is. I mean, it's nothing bad, right? It's just seeing now what terms cancel out or not. Okay, so for example, you just be careful that, for example, here you have p squared inside the brackets and here is p squared outside the brackets. So what you get is just the variance. Anyway, in the end, what you get is delta square, sometime t, in all its glory, it's going to be delta p square. This is the time 0 one. Mu square plus. Let me write beta here plus x0, plus delta x at time 0, where beta is going to be 1 over mu, and now this thing x p at time 0 plus 2 xp plus px. Okay, this just comes from before. Just trust me on this. Okay. Whew, so what does this tell me? It tells me that the variance increases quadratically in time, which means the following. So suppose that I start with, suppose that my initial state, let's put here, say of x squared, which is the, again, the probability of finding the particle in this position. And suppose it starts like very neatly a wave function like this. Let me do this in a different color. Okay. So this is like a probability distribution over x of the position of the particle. And let's say that this is time equals 0. And suppose it's now moving to the right, then at a later time, it's going to be, so here is my, this is the x0, right? And here I have my delta x0. And later on, it's going to be, for example, something like this. So time equals later. Okay, time larger than 0. Where here we have x of t, which is what? It's x0 plus p t. And this delta x of t is given by that thing up there. Okay. So this means that even when there's no external forces and you really just have the kinetic energy of the particle, it will still kind of spread out in the position basis. Whereas for the momentum basis, if you look at it, so here we have of p squared, it just stays exactly the same. Okay, so if it's a well-behaved thing, of course, if it's a very symmetric thing, so we have t equals 0, same as t large. Okay. Of course, if the initial wave function is not perfectly symmetric, maybe some things can happen, but in general, it looks like this. Okay. So if you look at momentum, very well defined, stays there, and the position it starts spreading out. Now, we want to apply this to a concrete initial state, right? Because now we just saw this applies to any state. And the states that you'll see in the tutorial this week, they are precisely states that that have this form that I drew here. So they are they're called example, Gaussian wave functions. So these will be states of the form where the wave function is, well, t equals 0. The initial wave function is going to be something like eikx, where this thing is going to be kind of the square root of what is a Gaussian distribution. You don't need to worry much about this right now. You'll see this in the tutorial. E minus over 4 sigma square. Where the nice thing about it, as you'll see later, is that it looks exactly like this. And this here is sigma, such that sigma square is the variance square on x. And of course, x0 is going to be your x. Okay, this is all at time 0. And the momentum is going to be h bar, this k there. Is going to be the average momentum. And the variance of the momentum, which will not change in time, it's going to be this. Okay, and we will see how this thing evolves in time. So this is just to tell you an example of now, it looks like we solved the system completely, but we still need to apply it to an actual state. Okay. And this state's called Gaussian things. This is because this is a Gaussian distribution when I have the wave function squared. Okay, probability distribution, they're very, very well behaved. They are thought of as approximations, as a particle that is as well localized as possible. And even in this case, you'll see that it does spread out. Okay, so in the tutorial this week, you'll do a few exercises just to get familiar with the Gaussian, and then later on you will evolve it for this thing. Okay, so today we just did the simplest possible Hamiltonian, the free particle. We saw how it, how x and p evolve. We kind of saw how to plug in an actual function to see this. Okay. And now next week, we're going to take maybe a more realistic example where we actually have some potentials or some forces acting on the system. And we'll see also the case with multiple systems. We could also do multiple directions here, for example, instead of traveling only in one direction, could be traveling in 3D space. Okay, so this was just the simplest example. And because it was the first one, we actually went and did everything by hand. Maybe in some later examples, I'll leave some parts as an exercise. Okay, thank you so much and see you on Thursday.